The first thing you need to do is you need to separate this out into two limits. Can someone tell me what this breaks apart into in terms of two limits? The limit as x goes to 3 of what? 2f of x minus the limit as x goes to 3 of... What can you do with that 2?
Put it out?
Yeah, pull it out. Exactly. You pull this out to here, so you get 2 times the limit as x goes to 1 of f of x minus the limit as x goes to 3 of g of x. Exactly, right. Now look, it tells you that f of 3 is 5, right? It tells you that they're continuous and f of 3 is 5. So what is the limit? Oh, it's 1. It's just it's a typo in terms of the pen, okay? It skips 3, correct. So this right here, what does that have to equal? Just that. It has to equal 5 because we know since it's continuous, the limit as x goes to a is going to be the function evaluated at 3. So this is 2 times 5 minus the limit as x goes to 3 of g of x. What's that equal? 4. So what do we now know? We know that negative the limit as x goes to 3 of g of x has to equal what? Negative 6. So that tells us that the limit as x goes to 3 of g of x is equal to 6. Correct. The key thing is, everybody, the key thing is this step right here. Here to there. That's because it's continuous. Because the function is continuous, the limit at the a value is the function evaluated at the a value. That's the definition of continuity we're working with. Okay, let's move on. So again, it's a step function, and the question asks, discuss the discontinuities. Are there any discontinuities? Yeah, where are the discontinuities? So at 1, 2, 3, and 4. This function is not continuous there because why isn't it continuous? Tell me why it's not continuous at these values.
Because it has different limits.
Why isn't, that's the question. Why not continuous here? Why?
Because there are different limits.
So what? Okay, so you're right. I'm not disagreeing with you. The limits are different on each direction. So what does that mean?
That means that there's no one singular limit.
So therefore, two different limits. So so I'll say it a different way. The left and right limits are what? Are diff. So what does that mean? So the limit does not exist at this point. So what does that mean about continuity? So not continuous at those points. So do you understand what we just did there? Because the left-hand, right-hand limits are different, the limit is said to not exist. And because the limit doesn't exist, we say that the function is not continuous there. If the limit is different, if the limit is different, the limit doesn't exist, so therefore it is not continuous at those 4 values. At those 4 values. Is the temperature at a specific location as a function of time, is that continuous?
Yes.
Why? Someone very clearly tell me why. Why is that a continuous function? Yes. What? Yeah. Yeah. So what does it have at 2? It's a jump discontinuity. So I don't know, we'll go from like this. Whee, and it jumps up to there. And a removable discontinuity at 4. So what do we need to make it for?
An empty dot.
An empty dot. Very good. There it is. Is it continuous oh wait, I just need to, what do I need to add to make this continuous everywhere else?
An arrow.
Yeah, and this goes wee like that, and it doesn't go straight down, sorry. There it goes. There's a jump discontinuity and a removable discontinuity. Make sense? Cool. Record this. Does this function intersect this function? Do they intersect? What happens if we tried to let's say we tried to solve this. What happens? The x's cancel, and what are you left with? 1 equals 4. Is that true? No, it's not true. So therefore, do they intersect? No. So what happens if you did this and you ended up with an answer like 6 equals 12? You would say, oh, they don't intersect. But is it possible for them to intersect? Yes. The question really is, when does it happen and how do we figure it out? This one, let's take a look at this rational function. This rational function, we're looking at this as x gets really, really big. What happens as x gets really, really big? What was it? It was 2x squared over what? What was it? It was 2x squared what? Was that it? Or what was that? I just can't remember what it was. Plus 5 over what?
Over 2x squared minus 5.
Like this, right? So again, we're looking at this, and we're really only concerned here because, yeah, 2 times a billion is big, but x squared is so much bigger. So if that's the case, if the circled red terms are the only ones that really matter, what's the limit as x goes to infinity? What do you think it is? Nope. Nope. Closer. 1. Why? Because 2 over 2 is what? 1. As x gets bigger and bigger and bigger, how important does the number 5 become? Not very, very important at all, right? Is this thing ever going to exactly equal 2?
No.
Maybe it'll cross, but as x gets big, it gets infinitely close to it because it has those little bits on the side, you know, the 2x plus 5s there, right? We okay with that? As x gets huge, the only terms that are of any influence are the ones that are circled. Those are called the leading terms. The leading terms are the terms that have the highest power. So if the powers are equal, you just look at the leading. So it's pretty straightforward. Horizontal asymptote. So if I ask, a horizontal asymptote is always a line. So in this function right here has a horizontal asymptote. What is the horizontal asymptote of that function? Y equals -1/2. The horizontal asymptote of that function is y equals -1/2. Let's make it a little bit more interesting. What happens if I did the limit as x goes to infinity of, let's say, x squared plus 2x over x cubed plus 5? Let's say I took this instead. What's different about this one? What's different about this function? The powers are not the same, exactly. So in that case, what's the only term what term is most important there in terms of size? X cubed. So the denominator is going to get much, much, much bigger than the numerator. So what is this going to be equal to? 0. The top is going to get big, but what's the bottom going to get?
Even bigger.
Even bigger. That thing will get closer and closer to 0. This is the denominator, this is the numerator. So here's the thing. If the degree of the numerator is equal to the degree of the denominator. So if the degrees are the same, what do you look at? Look at the leading, you said it over there, leading what? Leading what? Coefficients, yes. Sorry, the tablet's being a little cranky, but if the degree of the numerator is less than the degree of the denominator. So if the degree of the top is less than the degree of the bottom, what's the horizontal asymptote? Y equals 0. Done. That's all you need to remember.
And then if it's opposite, isn't that what it says?
What happens if the degree of the top is greater than the degree of the bottom? If it's 1 greater, you get a slant asymptote or an oblique asymptote. If it's more than 1 greater, it's none because it's no longer a line. It would be, you can have quadratic asymptotes, but what do we only look at? Asymptotes that are lines, asymptotes that are linear. Exactly, very good. Okay, square it, and that came up in the last class, and you absolutely can't square it because it doesn't equal anything. 3 over 5 does not equal 9 over 25. You can't just square something. It doesn't stay the same value. The truth of an equation stays the same generally, but a statement like this does not. What's the only thing you can mathematically do to this but not change its value? What can you multiply by and not change the value? 1. Do we actually multiply by 1? No, we multiply by a form of 1. We multiply by a form of 1. So the question is, and this is the big one, I'm telling you, you're going to multiply by a form of 1. It's not straightforward, though. Just watch for a second. You're going to ask immediately afterwards, like, why did you multiply by that? Well, or how did you come to that conclusion? We'll get to that. You see this right here? What's that just a fancy, what am I writing in a fancy way? 1. A over A is 1. Why is this helpful? Well, it's helpful because when we rewrite this, the numerator becomes 2x squared plus 1 over what? Over root x squared. What's the denominator become? over. Okay, so let's look at the denominator now. What's the square root of x squared?
X.
So the denominator here becomes 3x minus 5 over x. And here's a side note here. What's the square root of a over the square root of b equal to? The square root of a over b, right? Agree with that? So what does the top become here?
The square root of 2x.
You agree with that?
Yeah.
Have we changed the value of this statement?
No.
No. Let's keep on going. What does the denominator become? It becomes 3x over x minus. Do you agree with that?
Yes.
And this becomes 2x squared over x squared plus 1 over x squared. Do you agree with that?
Yes.
Can we cancel some stuff? Yep. The denominator becomes 3 minus 5 over x. And what's the numerator become? The square root of 2 plus. Have we changed the overall value? No. What are we doing of this? We're doing the limit as x goes to what? Infinity. By what I just told you, what does this go to? 0. What does this go to? So what does this limit equal? Done. It's clever, it's annoying, and I know it's not readily apparent, but the point is, the magical step, I left it in this form specifically because it'll have to go from this to this. Because I needed the same radical, I needed the same roots right there to press them together to get one square root. Because I had one square root, what could I do inside? I could simplify inside the square root. Again, 1 over root x over 1 over root x, x squared is just a form of 1. It just takes practice. It just takes practice. What you have to be comfortable with is trying different things. This is a new thing for you, I understand that. Let's look at another new thing.